So I guess the good news for you guys is we're almost done. Then you guys have almost completely survived. You've only got two things left. You've got a homework and you have the final exam. The homework, like I said before, is going to be due on Thursday next week, not Tuesday. Tuesday I'm going to be out of town giving a talk. So I encourage you guys to get together for studying on your own and do what you can. Also today, one other piece of business at the end, I need you guys to do the evaluations for the class. And so I need some volunteer to take this up to the dean's office after you're done. So I guess with that, I want to just kind of just get into the review, and then if there's any questions pop up or any questions you guys have over new material, ask me today, ask me over email, or ask me at the recitation next week on Thursday. And then, like I said before, I'll take the last problem set. I'll also take the bonus problem set if you want to give it to me there. If you can't get it to me then, I can take those as late as the final. But keep in mind, if I don't get them by Thursday, there's no way you're going to get them back to use to study for the final. If I can get them Thursday next week, there's a chance I can get them graded, and you can pick them up in my office on Friday if you want to use it to study over the weekend. Yeah, so however you guys want to do it, but that's just throwing out all the options. All right. No. I'm not going to penalize you. I'm just going to, but you know, you guys should have plenty of time between now and then. And also another thing is just my own feeling on it is that you don't want to be working on a homework all the way up until the exam, because it's going to take away your study time. So you're probably going to do better if you can just get it out of your hands by like Thursday and not think about the homework or doing the homework problems over the weekend, and you could just spend that time devoted to the final exam. All right, so what I want to get into today is, as you've noticed from the practice exam I gave everybody, there's only 4 questions on this one. I might do 5. I've done 5 before, but it'll probably be 4 problems like this. And if I do a 5th problem, it might be considered like a bonus problem. And so the topics you need to look out for is everything in the second half of the course. That's everything since the midterm. And that is linear algebra, tensors, which, remember, that just kind of flowed from linear algebra, Eigen value problems, and basically Eigen value problems, remember, that includes Green's functions. And then there is PDEs, special functions, and probability and statistics. So these are the big areas that you guys need to think about that are possibly covered. And what I'd like to do is just spend a little time today going over within these topics what are the kind of more specific things. Obviously, it would be difficult for me to come up with 4 problems that cover all 6 of these topics. So what you're going to do is, it's probably going to be 4 of them, and you can kind of play the odds a little bit on which topics are going to be covered, but I suggest, you know, study all of them and be ready in all of them. But focus on the main areas within each one. For example, within linear algebra, we did a lot of stuff with matrices, with linear independence, with vector spaces. We also did some stuff with curvilinear coordinates. You know, all of those things kind of play in with the linear algebra stuff. With the tensors, we did tensor operations. We talked a lot about the metric tensor and about different coordinate systems and about coordinate transformations. And so that was important. Within the eigenvalue problems, we did mostly eigenvalues involving eigenfunctions. So you had differential equations, usually ODEs, that had specific boundary conditions, and you calculated out what are the eigensolutions to that. And the Green's functions was essentially taking that a step further and using it to solve inhomogeneous problems. And remember, one way of doing that was actually doing a Fourier transform and an inverse transform. And then for special functions, for PDEs, the main thing that you want you to get out of PDEs was using separation of variables in order to turn your PDE into an ODE, and then also understanding that you have different classifications of PDEs and how to do how to use that to develop what kind of boundary conditions you're going to use. And then special functions came down to Legendre polynomials and Bessel functions, and understanding the generating functions of those. And then finally, for probability and statistics, a lot of that was understanding combinations and probability distribution functions and how to calculate means and and expectation values from probability distributions, particularly from like a Gaussian distribution. And so if you were given a problem, kind of like we talked about in recitation, where you got something that was statistically independent and being able to understand what that meant in terms of calculating the probabilities. I think I gave the example in recitation about where you have this group, and what they do is they practice birth control by essentially saying that as soon as they have a boy, they stop having kids. So if in the absence of that, 51% of the kids are born male. When you start applying the birth control technique, it has no bearing on the percentage of the born male. So it's the same 51% regardless, and the reason why is because of this statistical independence comes into play. So that's the overarching stuff that I want you to get out of it. What I would like to do now is kind of start diving into some specifics within these areas. And and I'm not going to go through and repeat the lectures exactly, but I want to kind of hit some of the high points from some of the lectures and some of the stuff we've covered in the class. And then, like I said, if there's any questions you can ask, or otherwise we'll just ask questions in the recitation.
As part of the Green's function, it could be like more derivation.
A lot of that is potentially just having you derive a Green's function, or in some cases use it. Like the example I gave last year in the problem was you had the Poisson equation, and you had to essentially derive from that the solution for potential given a certain charge distribution. And so that meant actually solving the Green's function for the Poisson or the Laplace equation, and then applying that with the stuff on the right-hand side of your Poisson equation in order to get the right formula. So the neat thing about that is you go from one well-known formula to another, but it's just kind of seeing how you get there. Okay. All right, so let me start with linear algebra. So within linear algebra, you've got, we talked a little bit about vector properties first. And this is basically how you add vectors together, how you have, you can subtract vectors, you can look at negative vectors as being basically taking the vector, turning it around, and having a null vector. And the idea is that when you do these operations with vectors, you get other vectors. So you can treat the vector as an object, and within the space you can go from having one vector to another vector. And so once you understood the basic properties of closure of vectors, this led to the idea of linear independence. And the idea of linear independence, we defined it as when you take scalar values and you multiply them by a bunch of vectors, and they sum up to 0. And if the only way you can make that happen is if all the scalars are 0, then you can say the vectors are linearly independent. And this led us to the idea of dimensions. In other words, like if you have a three-dimensional space, you can only have 3 linearly independent vectors and not 4. If you have a two-dimensional space, you can only have 2 vectors, not 3. And so once you got to this idea of dimensions, this led to the idea of having a basis for your vectors. And they had this thing called a basis vector that we used. And then that led to the idea of a coordinate system. So this is what I was trying to lead you through as we were going through the lecture. And so we would basically have our vectors that could be broken up in terms of the sum over all the dimensions for an n-dimensional space of components and bases. And so everything we did in linear algebra and a lot of the stuff we did in terms of tensors is all based on this idea that you could take these vectors and break them up into components and bases, and then you could do coordinate transformations on these to get into another coordinate system, or you could transform the components to give you something that looked like it was rotated or something like that. Now, this led to the idea of what we call the linearly independent function. And the idea of the linearly independent function is that you had these properties where if you applied a function to 2 vectors added together, it was like adding together the 2 functions applied to each vector independently or something like that. And so these linear vector functions, or sorry, I should say linear vector functions, not linear independent function. This linear vector function leads to the idea of a linear operator. And the linear operator is basically this thing that gives you the linear vector function. And then that led to the idea of the matrix, as we know it in linear algebra. And so once you had the matrix was sort of an object in the same way that a vector was an object, and it had all these properties. And these were things like addition of matrices, multiplication of matrices, having an identity matrix that exists, all those little things that you could do with these matrices. And so this was the point where we started specializing. And we said we're only going to use square matrices. And the reason why we use square matrices is because square matrices, you can multiply them in any order. and you can find an inverse matrix. And it just so happens that in physics, all we really do is use these square matrices. So we have an inverse. And so this calculating the inverse, I'm not going to go into it too deeply, but that was the whole thing where we use the cofactor and divide by the determinant, and so mathematically it's a lot of junk. But the point is that you can do more with it now. And then this got us into basically creating groups. Because once we were deciding we're only going to use the square matrices, we can get these groups. And we can classify matrices as things like Hermitian, or orthogonal, or unitary, or or symmetric or anti-symmetric. And based on what group the matrix went into, this led to certain properties of what we get out of it. And later on, this is kind of foreshadowing for when we started dealing with eigenvalues, about what the properties of the eigenvalues were going to be based on what the properties of the matrix are. So, we can use foreshadowing in here, even though it's not a literature class. So, once you can kind of put these things into groups, this is where, if we wanted to, we could have split off and started talking about group theory, which is what they would do in like particle physics. So, now what we were going to do is we're going to use these matrices, or these groups, and you can do all this stuff with them. And so this kind of took us, kind of down a parallel to the idea of coordinate transformations a little bit deeper. And the coordinate transformation is essentially some type of matrix being applied to some vector to give us a completely new vector. And so the coordinate transformations could be applied to a vector, it could be applied to a matrix, it didn't really matter to us. Then we kind of skipped over and we started talking about the scalar product. And the scalar product was basically A dot B, where you take two vectors and you dot them together and you get a third vector. Now, the neat thing is that because of the scalar product, this kind of could introduce the idea of vectors being orthogonal, where if these two vectors are completely perpendicular to each other, you get 0. Or since we're not limiting ourselves to just things that are in spatial dimensions, we can actually talk about this in terms of time or other dimensions, then orthogonal is just a better word to use. And then we can also got from that to the word orthonormal, which means it's orthogonal and it's normalized. And so that led, or came kind of in parallel to the idea of the basis vectors. And so all of this was essentially all kind of leading up to almost like a foreshadowing of getting into eigenvalues. And so I think I would like to talk about eigenvalues and then kind of double back to talking about tensors, just because I think this naturally leads in the eigenvalue stuff. Okay, so when we talked about eigenvalues, the thing that was interesting here is that everybody at this point should have been used to talking about eigenvalues, at least from the point of view of eigenvalues of vectors, where you have your linear operator and it acts on some eigenvector, And the result is an eigenvalue times that eigenvector. And this was neat to us because the eigenvectors automatically formed an orthogonal set of vectors. And so they were a natural basis. And when you transform your linear operator, or your matrix, into the coordinate system of these eigenvectors, then it naturally resulted in a diagonal matrix where the eigenvalues formed each of the terms within the matrix. So the eigenvalue problem, in a sense, formed a way of us diagonalizing the matrix, which is kind of a useful thing for the linear algebra, because now we can take any matrix, solve for its eigenvalues and its eigenvectors, use those to form a new coordinate system to base the system on, and then transform everything into a diagonal matrix, which is just easier to deal with. And I gave that example in class where we actually use that. And so this leads us to the idea of, well, we can do the same thing with differential equations. So if you have a differential equation and you add to that differential equation special boundary conditions that are well defined, the result is actually an eigenvalue problem. And so we can apply all the same stuff we knew about vector eigenvalue problems to these differential equation eigenvalue problems. And you can have orthogonal or orthonormal, just like you could have orthogonal vectors or eigenvectors. You can have orthogonal eigenfunctions. You can still have eigenvalues that come out from these differential equations, and you can also have a definition of orthogonality that comes in with these eigenfunctions. That actually comes from integrating the eigenvectors over, or eigenfunctions over the boundary conditions. And so the neat thing that came out of that was that there were functions, and I could define that here, is the dot product of these eigenfunctions is actually the integral over some boundary conditions of one eigenfunction times the other eigenfunction integrated over the value. And so we still get the orthogonality, we still get the complete set of eigenvalues and eigenfunctions, and because of the orthogonality, we can, just like we have a basis that's formed by eigenvectors, we can form a sort of a basis with the eigenfunctions and sum up the eigenfunctions. Any arbitrary function could be thought of as the sum of all of coefficients times each one of the eigenfunctions. And so you can create any function that obeys the same space in the same sense. And this is the basis for why it is Fourier series works. Because Fourier series, remember, are sines and cosines. And sines and cosines are basically orthogonal functions. And so if you sum up all the sines and cosines that are periodic orthogonal functions, then you can get every possible periodic function that will possibly work within that problem. And so this led us to the idea that we have two kinds of problems we can have. We can have a homogeneous problem, In a homogeneous problem is, for example, you have something like a minus lambda x equals 0. So it's a homogeneous eigenvalue problem. Or you could have an inhomogeneous problem. And the inhomogeneous problem is a minus lambda x equals y, where y is not equal to 0. And so this is the basic idea of homogeneous versus inhomogeneous. And if it's a homogeneous problem, in this case, it's essentially an eigenvalue problem, as long as you have those well-defined boundary conditions, or if it's a vector problem. If it's an inhomogeneous problem, then that's where we use Green's functions. So this is some of the main stuff that I want you to take away from dealing with these eigenvalue problems. Now for Green's functions, and remember this is the ugliest word you're going to hear in here. The basic idea here is that you have your inhomogeneous problem and you want to be able to solve it. And so the Green's function is a function where if you have your, let's say your operator, I'm going to say the operator is going to be u. And it's a linear operator. So if you have u of x plus k of x is equal to y, that is an example of an inhomogeneous problem. And the idea of the Green's function is that if g is the Green's function, then if you take u of g plus k of g, you're automatically going to get a delta function on the other side. And so the Green's function is the solution to your problem if you happen to have a delta function on the other side. Also, you can solve for your solution as being equal to the integral of the Green's function and, let's say, this y integrated over dx prime. So in other words, you integrate whatever's on the right-hand side with your Green's function, and the result is going to be the solution you're seeking. So it makes it really easy to solve this if you happen to know what the Green's function is. So the real problem with the Green's function is just figuring out what is the Green's function. If you knew the Green's function, then you really don't have a problem because you got the easiest thing in the world. All you have to do is solve one integral and you're done. And so in solving the Green's function, we talked about 3 different methods. One of them was the construction method. And the construction method is a quick and dirty way of doing it, not completely useful because you're basically dealing with an infinite series. And essentially the way it works is that your Green's function ends up being equal to the sum of your eigenfunctions divided by the difference between your eigenvalue and this other pseudo-eigenvalue that you have in there. And so when you do that, you have an infinite series. It's clearly a solution, and it takes advantage of the fact that this arbitrary function y is actually could be written as a sum of eigenfunctions. So in other words, every function can be constructed from eigenfunctions, and therefore you can construct this thing. Another technique we talked about was basically integrating the entire problem. And in that technique, you ended up with something where your function, you're using the fact that the Green's function is a solution. You have the delta function on the right-hand side. And when that happens, you basically get two solutions, a solution A and a solution B, where the solution A might apply on one side of your delta function and solution B applies on the other side of your delta function. And then you have to correlate the two somehow in order to make sure that you have a continuous function. Now this is a little bit better than the first one, and that at least you can integrate it because you can just integrate up to that point with one integral and then integrate on the other side with the other function. And the only real trick here is just basically finding what are A and B in order to make this thing work. And then the final way we did was the Fourier Transform. And what we did with that was we actually did a Fourier Transform of the function. So we went from like phi of x was the integral of something phi of k, and then later on we did an inverse transform. And so when we did the inverse transform of to transform an inverse transform of the entire equation, we're able to basically solve using the same kind of a variation of this integration technique in order to come up with hopefully a continuous function. And so these are three different ways to kind of get at a Green's function solution, and then once you got the Green's function solution, then you can just integrate and you're done. So, like I said, my concern is really about you guys having a big global picture about what's going on, and then figuring out the fine details about how to solve it, rather than you guys just being able to solve these fine details and getting completely lost in the weeds about what you're really going for. So the real goal of the Green's function is just to find the Green's function. Okay? All right, this brings us to tensors. Now tensors are another extension of linear algebra, where what we did here was we first introduced the metric tensor. And the metric tensor, usually abbreviated with a G, IJ, and it could actually be a function of position or something like that. And essentially what the metric tensor does is it provides a mathematical description of the coordinate system you're dealing with. So this ties directly into all that stuff we talked about with coordinate bases and stuff like that. And so we have two kinds of tensors. There's a metric tensor and there's an inverse tensor, or inverse metric, where we just have the indices up or down. The difference between these two is when the indices are up, we call that contravariant, and when the indices are down, we call it covariant. And for non-Cartesian coordinate systems, there's a difference between these two. Okay? And so the metric or inverse metric are often used to raise or lower the indices, which effectively means raising or lowering the where the indice sits on the components of your that form your vectors. So if you have dealt with this in the coordinate system, and you can now forget about all the bases and get back to what's going on with each one of the different quantities, then that's where the magic of this comes into play. And so we have these things called like a vector transformation, which is similar to what we did before in matrices, but here you could take a vector, and you can say that, well, that's equivalent to taking the derivative of one coordinate system with respect to another, and then contracting that with another vector. We're summing over J in this case. And then you could transform a tensor using something very similar to that. So this is equal to the sum over K and L of the derivative of x prime I respect to K and XL to the x prime J of BKL. So in this case, what's happening is you got this mixed tensor, and you're contracting it with two transformation matrices, where you can see the prime is in the top on one and the bottom on the other, in order to transform it into a new tensor in the new coordinate system. And so when we're talking about these, we have the tensor is basically any object that you have here. It's basically just the most general way of saying your mathematical object. If you have only one indice, then you consider that tensor to be a vector. If it's 0, it's considered to be a scalar. If it's 2 or more, it's considered to be a tensor. We just call it tensor in general. And so the number of indices equates to the rank of the tensor. So the more indices, the higher the rank. And you could do things like you could create a dot product as being a contravariant times a covariant, and so all of the operations we did before with matrices are the same. It's just that they're being expressed now in a different language. And also, I introduced a dot product, I introduced a direct product, I introduced the Levi-Civita symbol, if you guys remember. And that's essentially just an anti-symmetric thing that you could use in order to calculate things like cross products or determinants. Yeah.
In the practice again, you have a problem on there with proving that AIG with the AJ. So we just do performing the tensor transformations each one.
Yeah. 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 Like if you look at that one, let me look at that problem specifically. It was the last problem on the homework, and on the exam. And the basic idea here was we said that you've got a particular coordinate system where Aij is equal to Bij in this coordinate system. So the question was, are they the same in all coordinate systems? And so what you would do there is you would actually perform the coordinate transformation on each of them and show that, if it's true in this one coordinate system, then it has to be true in the next coordinate system, and so on. And so you can show that. It's basically just a proof, but it's essentially when you do a coordinate transformation on one and you get a new value, you can show that that same coordinate transformation should apply to the other one, in which case that means they're the same. It wasn't meant to be a trick question. It was meant to be something to make you think a little bit. Okay. Also, one other thing we talked about was the covariant derivative. And to get to that, we introduced the Levi-Civita, the Christoffel symbol. And the idea of the covariant derivative was that a covariant derivative is kind of like a special kind of derivative, denoted with these semicolons, where it's a partial derivative plus, or minus in this case, with an extra term added on to it, where this extra term involved the vector that you had and a Christoffel symbol. And so what this does is that the Christoffel symbol disappears in Cartesian coordinates, but in every other coordinate system you have a non-vanishing Christoffel symbol, and it forces your derivative to respect the curvature of your geometry, of your space. And so it's the equivalent of when you're taking a divergence in spherical coordinates as opposed to Cartesian coordinates, and how it looks more complicated when you do it that way. And so this is sort of what this does, is it kind of explains why it is you see that difference in a divergence or a Laplacian or something like that. Okay. All right, any questions so far? All right. I know we're flying, but I want to give you guys a little bit something different than when you had in the lectures, as far as just the kind of the 10,000-foot view of everything. All right, next I want to talk about PDEs. PDEs, the first thing we talked about with PDEs was, all the examples we give are second order. Maybe a few first order examples. And there was a very good reason we went into that, is because the fact that they were second order led to the classification of them. And remember, there were only three classes. There was hyperbolic, elliptic, and parabolic. And which class you had was going to determine how what kind of boundary conditions you could use. Whether you used Dirichlet boundary conditions, Newman boundary conditions, Cauchy boundary conditions, whether the boundary conditions were open or closed, all of that depended on what your classification was. And so that led to how do you solve it. And the way that you solve an elliptic equation and the way you solve a hyperbolic equation are going to be very different because of that difference in the boundary conditions. And remember, in the classification, if it's hyperbolic, then when you take your characteristic equation, which is essentially A times a second derivative of psi with respect to x plus 2b times the second derivative of psi with respect to x and y plus c times the second derivative of psi with respect to y is equal to some function of everything else. Then hyperbolic basically means that b squared is greater than ac. Parabolic is b squared is equal to ac. Oh, no, this is just f with some stuff inside. It's like parentheses. Yeah, and elliptic was b squared is less than ac. And, once you understand this, you know enough to classify the different equations, like the wave equation is hyperbolic and the Laplace equation is elliptic and so on. But essentially what this means is that when you have a hyperbolic equation, then you have real characteristics that you have to avoid, and there's two of them. When you have a parabolic equation, you have one real characteristic, and when you have an elliptic equation, there are no real characteristics. And so what that means is you have to be a little bit more careful under what conditions you can solve it, and that's what dictates the boundary conditions, and therefore how do you go about solving the equation. The other thing we talked about was separation of variables. And separation of variables basically means you take your PDE and you turn it into an ODE. And you do it with this technique where you would assume that each one of your variables is independent, and you can essentially write your solution, psi of, say, x and t, to be equal to x of x and t of t. And then once you've done that, you can plug that into your problem, and then you could just keep going from there. All right. So, I mean, those are really the only two things I want you to take away from the PDE stuff. I know it gets a little complicated otherwise, but that's the big picture stuff. All right, next we talk about special functions. And remember, this was that long lecture where we really didn't even have time to write everything down. But the two special functions we talked about, they were Legendre polynomials. Well, actually, I should. Well, I'll just write them, but using their symbols. There was the Legendre polynomials. There was the associated Legendre polynomials. There were the spherical harmonics. There were Bessel functions. And there were spherical Bessel functions. So all of these are just basically just different special functions that you might run into. The things that they have in common are that for Legendre polynomials, you can get to them from solving using separation of variables to solve a problem in spherical coordinate system. Yeah.
Can you repeat each one of those?
Oh yeah, sorry. Legendre polynomial or Legendre function, associated Legendre function, spherical harmonic, Bessel function, and spherical Bessel function. I guess this last one would be like plus 1/2 or something like that. And so the basic idea here is that each one of these is, the reason why they call it a special function is because all of these are basically form their own sets of orthogonal functions. Like some Legendre polynomials, they'll be orthogonal to other Legendre polynomials. Same thing with Bessel functions, same thing with spherical harmonics. And so because they're orthogonal, that kind of goes back to what we talked about with the eigenvalue problems. Also, another thing about them is that you can find their solution, again, based on the solving the like the Laplace equation and spherical coordinates or the or cylindrical coordinates. They can also be normalized since they're orthogonal functions, and so they could be used to expand out something like a Fourier series in order to cover all probable solutions. And another thing we had with them were recursion relationships, if you remember, because in that way you could actually calculate their derivatives by using combinations of other functions. So like a derivative of a Legendre polynomial could be written in terms of Legendre polynomials. So if you know all the Legendre polynomials, then you know their derivatives too. And then another thing about them is, let's see. Oh, generating functions. That's the big thing you need to know. And so the generating functions is really the big thing here, and it's about knowing how to use them. So for example, f of x and h could be written as taking the sum over L of P of L of x and h to the L. In which case, the Legendre polynomial is, or Legendre function, it's a function, it's a special function, it's not an easy function to deal with. H is just some value, or some variable, and f of x and h could be some analytic function which is really easy to understand. And so by using this generating function, it's kind of a compact way of carrying around your special function that you can unpack and use this to express the special function in different ways. So there was like integral representations of your special functions, there was differential representations. All of them were just all equally valid, and they all kind of came from doing something with these generating functions. Okay. So as far as special functions, I mean, those are the big things I want you to get out of it. And if you see a problem, like I gave you the bonus problems for the homework, and if you see a problem on the exam involving special functions, it's going to probably deal with either the generating function or the orthogonality of the special functions. So just be prepared on those two fronts. The final thing I wanted to talk about is the probability and statistics. And like I said, this is what I think most people consider the easiest part of the class. Where the way we looked at probability was that you looked at the probability as basically being the number of times that something happens divided by the total number of times. Okay? And so what happens is that we use probabilities a lot in science, and not all of them are probabilities that we can actually measure ahead of time. So we define two different types of probabilities. Posteriori, where this is a probability that comes from your measurements. And an example of that is, you know, biologists are doing the drug trial, so they have 1,000 patients, and they give each of them the drug, and they find out that like 90% of them it works for. So it says a 90% chance it's going to help you. The other thing that they have is a priori. And that is where you predict. And you don't measure, you actually just predict what's going on. In this case, you know, you're trying out a stunt which involves you driving your car and jumping over a ramp or something like that. Before you do it, you might want to figure out what is your probability of not dying. And so you can't just keep doing it over and over again and calculate that out. You need to actually look at all the different variables and calculate what is your probability of success from there. And so we'll make decisions based on either one of these. And so a lot of the time in science, what you want to do is you want to be able to use both of these and maybe use even combinations of both of these so that you can use your posteriori to measure probabilities, and then sometimes you're going to actually predict the probabilities based on other physical things that are going on. And so once you can calculate what these probabilities are, then I got into an algebra where you could, you know, we did the 4 different possible outcomes, and you're able to actually use these in order to come up with what it is, what is the probabilities in different situations, and so on. So I'm not going to repeat that from the lecture. So then we talked about 2 other terms. One was mutually exclusive. Mutually exclusive basically means that 2 things cannot both happen. In other words, the probability of you flipping a coin and it coming up heads and the probability of you flipping a coin and it coming up tails are mutually exclusive because it can't be both. It has to be one or the other. And the thing that's useful for that in our probability is we can just simply take the probability of one as being equal to the total number of successes minus the number of times the other one occurred. Then we have the idea of statistically independent. And the statistically independent means that, like, if we have two coins and we're flipping both of them, the probability of one coming up tails and the probability of the other one coming up heads are completely independent of each other. So just because you flip one coin and it comes up heads does not mean you're going to flip the other one and have it come up tails. And two successive coin flips are statistically independent. So these are kind of things that you need to know in advance when you're looking at any statistical situation. Is the probability that you're looking at, is it being something you're measuring, or is it something that was predicted? Are the probability of different things mutually exclusive? Are they statistically independent? And so once you get through that, you're through the probability part, and then you start thinking about combinations. And the idea of combinations is you have n things and you can arrange them n factorial different ways. And so what that tells you is that even though, for example, you flip a coin 10 times and it comes up heads 5 times, there are multiple ways that you can get the coin to come up heads 5 times. And so what this combination does is it allows you to kind of sum over all of the different possible ways that something could come out the way you want it to. And then you can use this to take into account whether or not order matters or whether order isn't important. And this gets us to what we call the binomial coefficient. Where the binomial coefficient was essentially n over m, written like this, and that was n factorial divided by m factorial times n minus m factorial. And so what happens here is that if order doesn't matter and repetitions are not allowed, then you get something like this, which will express all the different ways that something can happen. And so what we do is if we take this binomial coefficient and you multiply it by the probability of, you say the probability of success is m, then that would be equal to taking the binomial coefficient and multiplying it by the probability of success times the probability of failure, or 1 minus p times the probability of failure, where essentially this is the number of times you would expect to have a success, this is the number of times that you'd expect to have a failure, and to get exactly this number of outcomes, you get this, which is the binomial distribution. And so this binomial distribution is basically the mother of all the probability distributions. So what happens is you can take this binomial distribution, and if you assume that n and pn are large, so you have a large number of successes and a large number of trials, then this gives you the Gaussian distribution. Which is a distribution that you're familiar with from pretty much everything you deal with. And within the Gaussian distribution, you've got things like standard deviations. You can turn it into an analytic function and you can integrate. And so it's a lot easier to work with in a binomial distribution in order to get mathematical results that you can use. The other thing you can do with it is you can assume that n and pn, n is large, and Pn is tiny. So you have a very limited number of successes, and then in which case you get the Poisson distribution. And the Poisson distribution is also analytic, but it's a lot different statistics to work with. Because where the Gaussian distribution is centered around some fairly high number, the Poisson distribution actually looks like it peaks close to 0. All right. And then the only other thing we talked about was actually taking these distributions and making them into analytic functions, which you could use to find things like average value. So this is like the mean. Or define the variance, which is a sigma, which is equal to the square root of x minus x bar squared. Things like that. Or that's also equal to square root of, I think it was mean value of x squared minus x squared mean value. So there's a lot of different things this opens up in terms of using it to actually calculate the statistics of something, or the probabilities. And this is used a lot in, of course, statistical mechanics and then also in quantum mechanics. All right, so anyway, that was my review. And like I said, I wanted to kind of give you guys the overview of the second half of the semester. And so everything I talked about today was only from the second half. I didn't talk about anything from the first half, primarily because, I felt like everything that I talked about here built up on something from the first half of the class. So I expect that you've mastered that in order to get this far. Okay. All right, questions? Are there any questions? Or do you guys just need a nap? Time to refresh. Well, there's no class on Thursday, but you can all go eat turkey, so don't have to worry about that. All right. The last thing is I'm going to hand out the evaluations, which I need you guys to take care of, and then, and like I said before, if there's any questions developed, like now that you've kind of gone back and you've heard all the concepts again, if there's any questions over any of the concepts or any of the stuff that we're doing this semester, or how do you apply these to problems or anything like that, feel free to drop me an email, and I will do what I can, answer it over email, or I'll address it make a point to address it in the recitation next week, Thursday. But even though we're not meeting next week, I should still be responsive to email. Okay. All right, so let's get to this evaluation.